I'm Sebastian Zur, and I'm currently a postdoc at EDF. And the paper I want to talk to you today is the compressed oracle is a worthy adversary. And this is recent work with my former PhD supervisor, Stacy Jeffrey, at CWI and QSoft. Let's see, does this work? Ah, yeah, wonderful. So, okay, so suppose you want to ask yourself, like, given a room, or in this case, maybe a virtual room with many people, how many people do we need to kind of have in this room to find two people who share the same birthday with high probability, in this case, say 2/3? Classically, this is kind of well known. This is known as the birthday paradox, because the number is maybe much lower than you might expect in the first hand. And there's kind of an easy derivation to give a lower bound on the number of people required in this room. So what you do is you kind of keep track of the number of people that you've asked their birthday. So let's say after you've asked T people their birthday, you have T different birthdays. And you ask yourself, what's kind of the probability that after I've asked T questions, that I actually find colliding birthdays? What's the probability of this event occurring? And if you want to derive this, you can kind of split probabilities. So maybe you actually already had colliding birthdays after just asking T-1 people, and the extra question is just doesn't have a real purpose. But maybe really asking this last question was vital, and that's when you kind of found the colliding birthday. So if we kind of simplify this expression by bounding a few of these probabilities by 1, we see that we kind of get this recursive formula that really depends on kind of this probability, like finding a colliding birthday in the Tth query when you didn't have colliding birthdays in the T-1 query. If we assume that birthdays are kind of randomly distributed throughout the year, which may or may not be true, but let's do it for simplicity, then the probability that kind of this Tth birthday is going to collide with any of the former T-1 disjoint birthdays that we have queried, it's going to be T-1 over 365. So we're going to randomly sample a birthday, and it must match any of these kind of T birthdays that we knew before, which by assumption were all disjoint. And now we kind of have this recursive pattern, so we can do exactly the same with collision T-1 here. And that will give us T-2 over 365. And we can just keep kind of expanding this probability. And if you do that, you get kind of this sum, which sums up to the following expression. And if we want the probability to be high, say at least 2/3, then this shows you that having 23 people in a room with high probability, you'll have colliding birthdays. And this number is at least maybe intuitively surprisingly low, and this is known as the birthday paradox. You could, of course, generalize this. Say instead of sampling birthdays, you're sampling from some bigger set that's kind of a size n, and then you cover the well-known kind of collision problem. In this setting, kind of in this random setting where kind of each event happens with some uniformly random probability, then we know that classically the lower bound of solving this is square root of n, where n is the size of the domain we're kind of randomly sampling from. So this goes very kind of well classically. There is this nice analogy of just keeping track of all the information that you have. But of course, how are we going to do this quantum? So to that goal, today I want to talk to you about our recent work that kind of tries to have this nice classical intuition and tries to kind of map it in the current zoo of quantum query lower bound techniques. So first I'll give you a slight overview of some of the quantum query lower bound techniques. And then I want to delve into one of these techniques a bit more in depth, namely the multiplicative adversary method. Then I want to discuss a technique that actually comes from quantum cryptography, which seems to allow for this kind of nice intuitive reasoning that we just did classically, but then in the quantum setting. And then we show how we would kind of combine these two methods into our new method known as the multiplicative ladder adversary method. And then I'll quickly, at the end of the talk, discuss some of the consequences of these techniques and some results that we have derived. Oh, by the way, if there at any point anything is unclear or you have questions, please just unmute yourself and just shout, because maybe I won't see you like raising a hand or something, and then we can just discuss whatever you want to discuss. So we start with quantum query lower bounds. So we just asked the question, how many people do we need to find like this collision between two people? And we can generalize this question. We can say, how many queries do we need to some black box to compute some abstract function, calligraphic f, on every input in some subset of functions from x to y, with probability at least 1 minus epsilon. This question will exactly give you, the answer of this question is exactly the quantum query complexity of the problem calligraphic f with error epsilon. So to give maybe another example, our problem could be the problem of search, where x will be the index set 1 to n, and then y is a bit. So basically, the f here goes from n-bit strings, kind of functions where you input an index and then you get the bit 0 or 1. And specifically, I'm interested in a subset of all of these n-bit strings where the Hamming weight of f is precisely 1. These are kind of the more difficult instances in search, where there's only a single one, and I want to find this one in the bit string. So to compute f on any input means to really output this unique index in 1 to n that has the unique bit 1 in the string. So it's kind of well known that the lower bound matches the upper bound, and you can kind of solve this problem in square root of n queries. But how do you derive these lower bounds? Well, we have a lot of techniques to do this. One of the first ones was the original adversary method by Ambainis. I think maybe, oh yeah, that's right, in 2002. When I say lower bound methods, it means that the number that kind of comes out of this technique, it will be a lower bound on the actual quantum query complexity of the problem. So the quantum query complexity may be higher, and we're just giving like a quantifiable number that says this problem is at least this hard, and it quantifies that in the number of queries that are needed. So apart from the adversary method, we also have the polynomial method, which is even slightly older. Then later, the adversary method was kind of strengthened by allowing like some negative weights in the whole method, which is now when people say adversary method, that is usually the one they refer to. And then there's also this slightly more abstract, less well-known method known as the multiplicative adversary method. And we know that in the bounded error regime, namely when epsilon is a third, so that's what we just answered with the birthday kind of paradox, where we wanted with high probability, namely 2/3 that we found a collision, then we know that this negative weights adversary method is actually timed. It means if you kind of apply this method perfectly, then you will recover the exact quantum query complexity of that problem. But like sometimes in some applications, you actually care about the non-bounded error regime. So in this work, we'll kind of stick with instead of 1/3, we'll stick to an epsilon. And then there's actually reasons to go beyond the adversary method. And I have shown these methods here in this diagram with a reason, because we kind of know for some of these methods how they compare. So first, kind of trivially, the negative weights adversary was just a direct generalization by allowing for more freedom in your parameters in the original adversary method. So this one is strictly stronger. Later, this very abstract multiplicative adversary method was also shown to be stronger than the adversary method, which is a statement that doesn't make a lot of sense, as we just heard in the bounded error regime. But if you go away from bounded error, it's actually stronger, and you can do kind of better query lower bounds. We also know that this abstract method captures the polynomial method, which is quite interesting because originally the original adversary method and the polynomial method are known to be incomparable. There are problem instances where one always outperforms the other and vice versa. And in the case where epsilon is constant, we know that the negative weights adversary method is perfect, so it must encompass all the others. And recently, Bellows actually gave a constructive formulation in this bounded error regime, so showing how can I, given any kind of approximate degree polynomial, really translate this to an instance of the negative weights adversary method in the bounded regime. So what we see here, we have kind of a zoo of quantum Curry lower bound methods. And kind of if we go up in this diagram, they become stronger, meaning they give higher quantum Curry lower bounds. But this really comes at the cost of applying them. You will find in many kind of lecture notes about quantum computing, if they have a section about quantum Curry lower bounds, they will usually discuss the original adversary method and the polynomial method, and then people can apply them to, or students can apply them to, like the OR function or majority or these simple Boolean instances. But when we go away from this, we already go to the negative weights adversary or even the multiplicative adversary method. These become highly complex to apply. And like many of the papers that use the negative weights adversary method, they rely on a lot of representation theory, whereas usually the polynomial method can rely on a lot of Fourier analysis that we already kind of known for the classical regime. And the original adversary method is usually kind of a combinatorial argument, kind of count good instances versus bad instances. And for many problems, this is straightforward. But of course, for many of the problems where we currently don't know quantum Curry lower bounds, people have tried the easy methods, as it were, and we really seem to need the more difficult methods. So, to the goal of finding new. Oh, yeah.
Can I just so in the previous slides, are there like nice simple examples of problems that give these separations? For instance, between the adversary method and the negative weight adversary method, is like are these like simple problems or are they like contrived problems? Is what I was wondering.
Question. I think they're actually quite simple. So I think for maybe already like the collision problem, the original adversary method will not work.
Right. Okay. And the negative weight one works for collisions?
Yeah, negative weight one works. But it's super convoluted. So the lower bound for collision finding, we knew it due to, I think it's Aronson and Shi, who did it using the polynomial method.
Right.
And then I think maybe 12 years later, Bellows and Rosmanis gave a negative weights adversary lower bound, which was like 30 pages of representation theory.
Oh my god, okay.
Yeah, and now we're really just talking about the collision problem. Right. So if that's already kind of too hard, well then with any more interesting problem, then it already becomes very quickly unfathomable.
Right. And these work in worst case instances as well, I suppose, right? In the sense that they're not assuming any distribution, unlike, I guess, the compressed oracle that we use, right?
Exactly. They really work on any input distribution. I guess for the polynomial method, you're restricted to Boolean functions. But in the adversary methods, they work on any distribution. And usually, somehow, under the hood of these methods, what you usually do is you take a difficult instance. For instance, in search, we take the string with Hamming weight 1. And then we somehow turn this into a distribution. So for instance, it could be all strings of Hamming weight 1. With collision, like if you look at the adversary method kind of proof for collision finding, they look at really like a distribution over functions where you get one collision precisely. Which are the hard instances. Of course, having many collisions would only make the function kind of more easy.
Right.
But indeed, like that's good, and we'll get to that when we discuss the compressed oracle method. But indeed, these work for any distribution of inputs. So whatever makes the function kind of hard, you can try to classify that in the input distribution.
Okay. And what problem is there also a simple problem that separates the multiplicative adversary method from the other ones, or like say for example from the negative weight adversary method?
Oh, sorry,
like a simple problem.
I disconnected a bit. So could you
Oh,
repeat
sorry.
the question?
Sorry about the connection. So I was asking if there's, just as you said, collision separates adversary, the negative weight adversary from adversary. I was wondering if there's a similar problem that separates multiplicative adversary from negative adversary.
Ooh, so that's a good question. So with that, we don't know. So we actually we know that the adversary method kind of fails for exponentially small epsilons. Kind of that's where it goes wrong, but it's not specifically a problem that goes wrong. So the negative weight adversary method just doesn't work in the formulation when epsilon becomes kind of exponentially small. So in that sense, already any problem would be an issue.
I see.
And what will be the issue is specifically the dependence on epsilon. So if you get rid of epsilon, if it's constant, we know it's tight. So the only gain you get from negative weight to multiplicative adversary is really like the dependency on the error in your resulting quantum query lower bound. And like there are not many instances where this is super useful, but we'll see later that we in this work we want to study also a strong direct product theorem, and that's where you really need exponentially small probabilities of success.
Okay, thank you.
Yeah, you're welcome. Any other questions? Okay, then I'll move on. So yeah, as I was saying, if we kind of go up in this diagram, we get stronger methods, but much more complicated to use. And kind of in an ideal world, we would be able to construct quantum query lower bounds in the same very intuitive and combinatorial fashion as we did in the birthday example at the beginning of this presentation. Like, there's of course no reason why this should be true, but this would happen to us in an ideal world, and we will be able to produce many quantum query lower bounds. So what I want to be able to do is somehow keep track of these queries that I've done and the resulting answers that I've gotten, and then do some combinatorial analysis to get a lower bound. Now I'm going to dive a bit into the strongest of the methods that I've just described, the multiplicative adversary, and I'll try to give some intuition as to why it is so difficult to apply to any problem. So to discuss this method, I'm going to kind of set the stage of the model that we're using. So we're trying to lower bound the quantum query complexity of an algorithm. So what this algorithm has is it does queries. These are these kind of O unitaries, and they're the only ones that can interact with some randomized input F. And in between these queries, we allow the algorithm to make any kind of unitary on its local system. So this local system is given by X and Y, which will be used for the queries, and then some working register W. And there is no bound on kind of how strong these local unitaries can be. They can do whatever. We're just counting the number of oracle calls. So F is distributed according to some distribution of inputs. These can be hard inputs. These can be easy inputs. And then our oracle is the only operation that allows us to access this random function. And how the multiplicative adversary, but even the other adversaries methods work, is what we do is we purify this randomness. So instead of our oracle being some random instance, what we're going to do is we're going to purify this into a quantum state that really encodes the distribution into its amplitudes. So we're going to get a superposition over inputs where the amplitudes are precisely the square root of the weight under this distribution. And if you do this, our oracle changes as well. So we just get an extra register. And then controlled on this register, controlled on the input F, it actually applies the phase in front of it. So this is kind of the input model that we're dealing with. And what we're interested in is kind of looking at the state of the algorithm after each query. And we try to look how the state changes. And we try to extract some information from that to actually give a quantum query lower bound. So more specifically, instead of looking at the joint state of the system, what I'm going to do is I'm going to trace out the algorithm side, and I'm going to just look at the reduced density matrix of the input. So at the beginning, before we have done any query, we are not entangled. There's no entanglement between the algorithm and the input register because no queries have been made. So this row 0, if you trace out the algorithm part, it's just this initial state delta. Nothing has happened yet. But then, as this algorithm is going to make queries, these density matrices are going to change. And at the beginning, this row 0 just being the projection onto delta means that the algorithm knows nothing except for what the initial distribution is. But then as the algorithm progresses, somehow this row t should have enough information to, with high probability, output the correct answer to our input. Now this is all very hand-wavy, and now this multiplicative adversary method is going to try to formalize this intuition. So we're gonna now construct some kind of progress measure that really allows us to say how close are we to outputting the right answer. This progress measure is going to rely on something that we call the adversary matrix, or in this case, the multiplicative adversary matrix. And in its most abstract sense, it's just a Hermitian operator. So I have his eigenvalues here by small lambdas, and then the projection onto its eigenspaces by the big lambdas. And it has to satisfy a few properties. So first of all, it's positive definite with smallest eigenvalue 1. So I'm going to assume that lambda 1 is 1, and then all the other lambdas just become bigger. And second of all, I want my initial distribution to be in the one eigenspace of my gamma. And these properties are derived with a reason, because now what happens is we can define this progress measure. So we take the trace of our reduced density matrix, rho t, after multiplying it with gamma. So what does this mean? Well, at the beginning, this trace will be precisely 1, because we know that rho 0 is just a projection onto delta, and delta lives in the one eigenspace of gamma. So if you take this trace, you're just left with delta, and the trace of that state is 1. So at the beginning, our progress is 1. And you can prove that if we want the algorithm to succeed with high probability, at the end, it must be some function of epsilon that is much bigger than 1. And this exact function is just characterized by the success probability of the algorithm. So we start at 1. We must end up at something that's much more than 1. So what we just try to do is we try to capture how much progress can we make with each query. And it's called the multiplicative adversary matrix because we look at the multiplicative progress. So we take the ratio between this progress measure, between the tth minus 1 query and then the tth query. So if you know that it needs to become some function kappa epsilon, it starts at 1, then you can kind of deduce that the query complexity t must be at least the logarithm of k divided by the logarithm of c, where c is this maximal progress that I can kind of make with each query. So this, in kind of from a high-level overview, is the multiplicative adversary method. But the reason why we actually never use it to derive any quantum query lower bound is that it's very difficult to bound this c. So first of all, you even have to generate some abstract adversary matrix gamma, and it's not immediately clear how these eigenvalues and eigenspaces really relate to the underlying problem. And you can maybe imagine kind of a nice gamma, a gamma that's intuitive to make, but then like how are you going to upper bound this progress ratio between the trace of gamma and rho t? Like this is, in practice, it's very difficult. And in the original paper that kind of makes this method, already just doing search is very difficult. Like the analysis this goes through is very non-trivial. And if you compare this to, say, the adversary method for search or the polynomial method for search, this is elementary. You'll find this in many lecture notes. So you pay a very big price in simplicity for the power that that method has. Because this method captures every quantum query lower bound method that we currently have. So can we somehow make this method easier using the combinatorial intuition that we had in the birthday paradox.
Sorry, before you go on, can I ask a question?
Yes, of course.
Right. So there's two things. So one is a dumb question. Well, both might be, but one is certainly dumb, which is that the adversary method. Why is it called the adversary method? I never fully understood. Like, who's the adversary? I never really got the intuition.
Yeah, that's definitely not a dumb question. So I think in the original paper by Ambinus, I think there is a sentence somewhere that he says that we can choose the input distribution adversarially. I think there's something like this.
Input distribution over the instances that you want to lower bound.
Exactly. Yeah. So whatever gamma you might think of, it must be able to really deal with like the hardest possible input distributions. And I think this is why he calls it an adversary matrix. But definitely in the original paper by Ambinus, I remember there's like some motivation why he calls it the adversary matrix.
But this so just so I understand, this adversary matrix is not what we're thinking of being as chosen adversarially. It's the somehow it's response to the input distribution.
Yeah.
Okay.
But I think indeed, especially coming from like say like cryptography, it's very weird to call this an adversary. Because this gamma actually it helps us. We choose it to kind of get the I think it's just Ambinus came up with the name and we just stuck to it.
Right. Okay. And the other question I wanted to ask was because it's been a while since I've looked at these. So the additive adversary method is instead of the bound, like you instead of looking at the ratio, you look at the differences. Is that is that how it was?
Exactly.
Okay.
Yeah. So you look at the differences, and then you still start at 1, but then you want to get very close to 0, kind of depending on the error. So instead, your eigenvalues are actually going down, I think, and you're trying to make the progress lower. I think there the progress it's more intuitive, that it's about how well you can how close to states of different inputs, how well you can kind of differentiate them. Whereas here, it's really something more abstract. It's really just this trace between these two instances, and it's not clear how this really directly relates to distinguishing different inputs. But the analysis works. Weirdly enough, even though they're different measures of progress, you're not just indeed switching the multiplicative ratio to an additive ratio. Even like you go from 1 to something big instead of 1 to 0, you can still show that this fully captures the negative weights adversary method.
And sorry, just a quick follow up to so in the adversary method, the matrix is essentially the same, except that maybe the eigenvalues have a different range. Okay. And in the negative adversary method, I guess you can also have the eigenvalues be negative. Is that the idea?
I think so, because you just don't want the eigenvalues to be 0. I think that's the only thing. Yeah. Oh, wait, no. So let me be clear. So I think actually the way you make the adversary matrix in the negative weights adversary is you actually construct it element by element, and then you allow for negative weights. But I guess having negative weights there kind of corresponds to allowing negative eigenvalues.
Yes. And here the eigenvalues are 1 and more than 1, right?
Exactly. Yeah. And even though that might seem like a restriction, this is really the most general method we have.
Nice. Okay. Thank you. So, sorry for the interruption.
No. Please go ahead. It's nice. This makes it interactive. Makes me feel more like I'm there with you guys. Okay. So like we just saw, this is a very kind of difficult method, and we want to have something that's a bit more intuitive. And this is where something surprising happened in the literature, because actually a technique originating from quantum cryptography seemed to suddenly address this intuitive question. So I want to discuss it now and show how it kind of relates to the other quantum query lower bound methods that we have. So,
hello, Sebastian.
yeah.
I have a question. So I don't understand these things, but like it's related to the. Can you go to the like previous slides, like previous slide? Yeah, the previous one.
Oh, sorry, this one.
Yeah, this one. Yeah. So so one thing that I'm having a hard time to understand. So the thing is like gamma is lower bounded, so it does not have any upper bound. So I'm thinking like this when you are taking this maximization over gamma. So how are we like assuming that it is finite? So like this.
Very good point. So indeed, if you make gamma bigger, what's going to happen is you're going to make both the top part of this fraction bigger. You're going to make this kappa epsilon bigger, but you're also going to make this ratio bigger.
Okay.
So by kind of scaling gamma up or down, you're not really changing this ratio a lot.
So C is not a constant.
Oh, so no, sorry. Yeah. Oh, that's very good. Yeah, C is not a constant. It's really just some upper bound that we have on this ratio, and it's inherently dependent on gamma.
Okay. Yeah. So I was thinking.
But C seems to be. Sorry, C seems to be independent of the norm of gamma, right? In the sense that if you scale gamma by some constant, C would remain the same, right?
So you would hope that because somehow you're kind of maybe dividing over gammas. Yeah. But this can be tricky in the actual kind of lower bounds.
Oh, really? Okay.
You're really dividing over these traces. But indeed, like if it was literally just multiplied by a constant, then indeed, then by linearity of the trace, it kind of cancels out. That's true. But that's why, like, just making gamma kind of globally bigger or globally smaller will not affect this. But what will change it is kind of the way that these lambda i's are in size with respect to each other. So do you make maybe a very big jump from lambda 1 to lambda 2, and then just small increments when you go up? Or are they kind of evenly spread out? These things do impact this ratio. And because we're kind of not making a distinction between the different t's here, we just kind of upper bound it for general t. In the best sense, you want all of these progress ratios to be very similar. Because if there is one progress ratio that's very big and all the others are small, if you're upper bounding by the biggest one, then probably you're going to kind of lose some tightness. But indeed, like gamma, like I could make the largest eigenvalue, I could make it infinitely large. And actually, in some of these reductions, not in our work, but in previous works, people do take these lambdas to maybe go to infinity. And they do some analysis in the limit and then show that it's maybe weaker or stronger than another method. But great question.
Maybe I can add that what I said earlier was a little bit wrong because you're somehow normalizing the global weight of gamma by saying trace gamma rho 0 is 1. So I don't suppose you can just arbitrarily scale gamma with a constant anyway. Yeah. So, sorry. Yeah.
I guess you could scale all the other eigenvalues except for the first one. I guess that's possible.
Yes. Yeah. But then the ratio may not stay. Yeah. Sorry. What I said was wrong. It doesn't. Sorry.
Are you? Yeah. I didn't notice it as well. Okay. So let's see how we can make this kind of nicer, more intuitive. Here. Great. Okay, so like the solution seems to have come from quantum cryptography, where if we look at this collision kind of problem, remember that we just did a combinatorial analysis kind of that depended on the kind of input and output to our queries that we kind of kept track on. And what we would like to do is and so this probability of success really kind of only depended on this incremental success probability where we didn't find our answer after t-1 queries, and we now want to find our answer, our collision, in the tth query. And so how would we do this in the quantum case? It turns out that if you put some restrictions on the input distribution, so kind of the more general restriction is that delta should be IID. So querying x1 and xj is kind of independent of each other. Maybe just for intuition, just think of that kind of each query is just a uniformly random sample, but it's deterministic. So if you query the same index twice, you'll get the same answer. You could, for instance, think in the search instance that every index with probability 1 over n can be a 1. So you query index 1, and if it's a 0, if you were to query it again, you would always still get 0. But every new index that you query, independent of the number of the Hamming weight you've already found, it will always, with probability 1 over n, give you a 1. So if we are restricted to this setting, which is definitely a severe restriction, then we can kind of make this whole argument quantum. So now we have these kind of input-output quantum states that keep track of the indices that we've queried and the answers that we've gotten. And as we're kind of used to quantum, we just get square roots over everything. And you could see it kind of by following this analysis that if I put square roots over everything, I now find this new lower bound, which is indeed the quantum query lower bound for collision finding. And I'm, of course, putting kind of a lot under the hood here. But I want to discuss a little bit why this works, why we're allowed to kind of keep track of these input-output pairs, which after T queries are kind of at most T input-output pairs. Because clearly in the quantum case, what makes everything so difficult is that you can query in superposition. So instead of just kind of querying just deterministically just single indices, I can do things in superposition. Things might interfere. But somehow this compressed oracle technique formalizes that as long as you're in this restricted input distribution, kind of the original intuition still goes through. And the reason is as follows. So this is maybe the most famous kind of query model that you know. And it's kind of the bit query where we put the answer of our query, so f of x, into the y register. And usually this plus is like up to some like group action model or something to make sure that we don't expand beyond the maximal register size. So this is the bit query. And in many kind of quantum computing lecture notes, you'll find that sometimes it's much more convenient to work with the phase query. So in the phase query, what I'm doing, I'm just going to change the basis of this y register to the Fourier basis by applying a quantum Fourier transform. And I'm going to denote this basis change by this little hat on top of y. So this now means that y is in the Fourier basis. And if we do that, we actually get a phase. So instead of putting the answer into the y register, there's now some global phase on the state that depends on f of x. And here, just for kind of clarity, when I write ket of f, you should see this as kind of a truth table. So it's actually what is the value of f on the input 1, tensored with what is the value of f on the input 2, all the way up to kind of the final input that I can plug into f. So it's kind of a quantum state encoding in tensor product, which we can do because it's independent of each other, and kind of a big truth table of the function. At least to me, when I learned about this phase query, I always thought implicitly that this phase belonged to x and y. Because, well, clearly that's the algorithm side. Like, if I'm doing anything, I'm just changing things on the algorithm side. I'm not changing anything on the input register. That's just some black box that I have access to. But clearly, if you look at this from a mathematical perspective, this is a global phase. So what I can do is I can pull back this phase not into the xy register, which I could do by just reversing this Fourier-based transformation, but instead actually applying a Fourier transformation on the input register. So if I do that, if I now change f to be in the Fourier basis as well, so now both I and f are in the Fourier basis, this phase is pulled back into the input register f. And what I mean with this notation is kind of nothing has changed except precisely kind of the xth part of our truth table. And there I have subtracted y. And everything here is still in the Fourier basis. So by doing this basis transformation, we're really going from a setting where a query changes something on the algorithm side to a query actually changing something on the input register side. And this, I think, intuitively should be very weird to you, because this input, it should be some immobile object that we just have access to. We're querying it to get answers. But just because of the symmetry of the oracle operation, like, you could review this as well as actually the input changing depending on the queries that we're making. And this is wonderful, because by doing this, remember that in the adversary methods, we're keeping track of the reduced density matrix on the input register side. So by viewing queries in this model, now we can really see what a query does to this input register. And this beautiful observation was done by Gendre in 2019, and this really made the compressed oracle technique. And what's very interesting is that quantum query complexity people, so the adversary method came from 2002. So we had been working with this for 17 years, and no one ever noticed that you could just pull back the phase. So I think that's a truly wonderful, simple yet kind of strong observation. And it allows you to make the following argument. So at the beginning, if our input distribution is uniformly random, if it's just delta, then if I change this into the Fourier basis, well, the uniformly random superposition in the Fourier basis is just head zero. And I know that all of these are IID, so it's actually just a tensor product of ket zeros. And then with every query, what happens is I can change one of these indices. So if I only do T queries, my rho T will be supported on basis states with at most T of these indices, of these entries being non-zero. And this is really the formulation in the quantum case of what it means to have T queries and to only have T input-output pairs, but then formalized in the quantum case. So it's really the support of rho T is limited. So if you look at kind of the entire Hilbert space that my input register could occupy, we know that we start at the pure state rho zero. And then slowly by making queries, we can exist in some bigger subset of our Hilbert space, but it's very clearly still not the entire space. And the compressed oracle technique really uses the fact that you know that you live in a significantly smaller subspace to make a sharp quantum query lower bound. So in this sense, what you're actually doing is you know that you're in some subspace where you haven't found a collision in T-1 queries, and you're effectively looking at the success probability of, okay, I now make a query. What's the probability that I now land in the collision part after T queries? And we've seen before that classically this is an easy combinatorial exercise, and you could actually just do the same analysis in the quantum case as well, as long as you don't forget to put a square root on top of everything. So this is beautiful. This is a really nice way to do quantum query lower bounds. The problem is that for many instances in kind of the instances that we quantum query complexities care about, our input is not uniformly random. So in cryptography, maybe you want to prove security of some cryptographic construction that involves a hash function. We then model the hash function as a uniformly random function, and now we can just do this analysis. So then you could show that finding a collision in a hash function, it's quite difficult if you don't make enough queries. But in quantum query complexity, we're, for instance, interested in the element distinctness problem, where usually there's only a single collision, and you have to find it. And this makes the input no longer random, because you know, for instance, that if I found multiple indices that have no collision, then the probability increases for every new index to actually contain a collision, because the input has a certain promise. And in the uniformly random case, it does not. So how can we take this compressed oracle intuition and try to kind of stitch it back into the original multiplicative adversary method. We managed to do this successfully in this work, and we get a new method that we call the multiplicative ladder adversary. So now I'll show you how this kind of intuition can be put into the multiplicative adversary method, and how we can get these kind of compressed oracle type bounds. So remember that this was kind of the setting of quantum query lower bounds that we had before, and now there's this new method from quantum cryptography, and we want to know where it lies in this kind of zoo. So then the question is, okay, what could be a possible kind of method that is stronger than a compressed oracle? And if we look at the few attributes of these quantum query lower bound methods, then we had the strongest one, the multiplicative adversary method. It can do everything, so it works for all input distributions, and it also satisfies a strong direct product theorem. So what this is, a strong direct product theorem, it allows you to, if you have a lower bound for computing one instance, so you have an upper bound on the success probability of computing one instance, then you actually know that computing k instances, it just gives you a kth power of the success probability. And it says that you can do nothing smarter than this. K instances that are IID, you just get this p like multiplied to the power k. And if you want to do this kind of successfully, well, clearly, even if p is constant, now you're getting a constant to the power k. So to prove these kind of methods formally, you need your error, it needs to be allowed to be exponentially small in k. And this is really where the negative weight adversary method fails. So it can't be used to prove a strong direct product theorem for quantum query complexity. However, this method that I just described from cryptography, it can. People have used this to show kind of strong direct product theorems. So clearly, if we want to generalize the compressed oracle method, it probably won't be generalized to the negative weights adversary matrix method, and instead we have to generalize it to this very abstract, very general multiplicative adversary method. But how are we going to do that? So remember that we have this very abstract gamma that has no relation to the problem whatsoever. What I'm now going to do is I'm going to envision that these eigenspaces of gamma actually live on a ladder. So we start on the ground with lambda 0, and then kind of at each step up the ladder, we move up one eigenspace. And I want to formalize this. So first of all, the steps on the ladder should be evenly spaced. And this is captured by, I want my eigenvalues lambda to just be powers of some kappa bigger than 1. So this is gonna, if I want to now deduce how hard it is to climb up this ladder, well, if there's one step that is much more difficult than other steps, this is going to be very difficult to kind of get a good bound. So somehow I want to say, okay, all these steps on this ladder, they're evenly spaced. More importantly, you are also not allowed to jump. So with every query, you can kind of move up or down at most a single step on this ladder. So if I am in some lambda j and I make a query, there will be no overlap with kind of any of the lambda I that are at distance further than 1 removed from this lambda j. So if I do a query, I just spread out very locally. And this is why we call it the multiplicative ladder adversary matrix. So this is kind of intuitive simplification 1 that we make to our multiplicative adversary matrix.
Sebastian, sorry, can I interrupt a bit?
Of course.
So these you're writing as constraints that are satisfied, but I suppose you have an actual construction that satisfies these things, or are you saying that there exists some multiplicative adversary matrix that satisfies these? Like, I'm asking if there's like, if it's a constructive thing, or is it like a demanding?
No, it's just purely demanding. Yeah.
Okay.
But we show later that actually, so for instance, the compressed oracle technique or the polynomial method, you can take an instance of those and actually transform them into a multiplicative ladder adversary. But indeed, we have no recipe how to kind of do this in general, or also we don't have a proof that for every gamma you could always massage it into a different gamma that has this form. But what's actually funny is we found in the literature that every example or lower bound that exists from the multiplicative adversary matrix is actually of this. Yeah. So somehow it seemed to have been the canonical form. And I think it's also because if you're not in this form, then it's very difficult to make a bound. And we showed that, well, if we assume anyway to be in this form, then the analysis can be much more simpler. So I guess we have this very strong framework and we only use a very tiny part of it. So now we just zoom in on that part and really make abuse, I would always say, the fact that we're in the tiny part. And that allows the method to be much more simple.
Right. Okay. Thank you. And you, I guess you'll explain how the compressed oracle has relation with this. I guess that'll come. Okay.
Yes. Yeah. We'll get to it very shortly. Yeah. So this is, I would say, simplification number one, is we make the gamma easier. But what I also want to do is in a compressed oracle, we could really say, hey, after T queries, we're in kind of a smaller space. We're not in the entire input register. It kind of grows with every query. So I'm going to do this as well. What I'm going to do is I'm going to project onto the span of rho T. Kind of what can rho T be for any possible quantum query algorithm that makes T queries. And I'm going to project onto that span. And in the paper, we actually show explicitly what this span is. But if you're interested, you can take a look at it. But I think it will be a bit too technical to discuss it now. But this projector is really properly defined. Like we know exactly what it projects onto. And what I'm going to do is notice that I can just insert it into the progress measure for free, because it projects onto the span of rho T. So I can always kind of multiply it with rho T and I don't change anything into the trace. And this allows us to really kind of use the fact from the compressed oracle technique that after T queries, we're in some limited space of quantum states that are that you can reach within T queries. So remember that the problem of the multiplicative adversary method is we have no clue how to bound this kind of progress ratio efficiently in many instances. But if you use the ladder simplification and this kind of rho T simplification, then we can upper bound this by this following quantity. And if you look at it, there is already kind of the ladder structure, because we're really looking at, say I start in lambda I, and I'm within T-1 queries. Then after a query, what is kind of my amplitude on the next step of the ladder? And this K is exactly the space that we have between these ladder steps. So here is kind of the parameters that you can change. You can change what are the steps on the ladder and how far are they distanced between each other. And note that this looks very similar to our compressed oracle bound. So we really have, we're in some lambda I, which could be not having found a collision. We're within the case where we've only done T-1 queries. Now we're going to make a query, and we want to lay in the next eigenspace, which could be precisely having found the number of collisions within T queries. And this is kind of the intuitive picture how the compressed oracle technique will reduce to our multiplicative ladder adversary method. And in the remaining time that we have, I want to kind of enumerate some of these results that we have with this new multiplicative ladder adversary method. So first of all, kind of we have this new method, and we show how we can plug it into this picture. So our new method fully encompasses the compressed oracle method and the polynomial method. And then because we look at the subset of all possible multiplicative adversary matrices, clearly it's kind of weaker than the original big method. And it allows for now a kind of a connection of the compressed oracle method into this zoo of quantum query lower bound techniques. So how do our reductions go? I will kind of give you a quick kind of high level intuition. So for the compressed oracle technique, we already saw that there's already this kind of nice duality between the bounds from the compressed oracle technique and our bounds from the multiplicative ladder adversary method. So really, like if we formalize this, our lambda 1 pi t space will literally just be spanned by states, like up to size t, so up to like t input output pairs, where actually there is a collision. So here I've put it in the first two, kind of birthday 1, but the collision could have occurred anywhere. And then like our lambda 0 will be precisely where we haven't found the collision. So all of these outputs in the input-output pairs are distinct. So this is kind of a straightforward mapping between the two. But for the polynomial method, something more interesting happens. So I'll just do a quick recap of the polynomial method. So what the polynomial method says is, if we are dealing with a Boolean function, we can define its approximate degree, which is kind of the smallest polynomial in the sense of its degree that approximates our function very well, like up to error epsilon. This is known as the approximate degree of a function, of a Boolean function. And then we know by the polynomial method that up to some constants, this approximate degree is a lower bound on the quantum query complexity of f. So how will these degree p polynomials kind of map to our multiplicative ladder adversary? Well, we need the following observation, which was already known in the literature, namely that if you look at the space of states that is reachable after t queries, then these are precisely polynomials of degree at most t. So what this means is they already have some kind of nice ladder structure. So kind of with every query that you make, you can only make this polynomial at most 1 degree larger. So not only does that already give us a nice definition for our kind of projections onto the span of rho t, but in fact, we already have a nice ladder structure for our eigenspaces as well. We namely let these ladder eigenspaces be precisely the polynomials of degree I. So we start in like a 0 degree polynomial, and then we kind of slowly move up the stairs, getting bigger and bigger and bigger polynomials. And it turns out, like, if you plug this into our method and then kind of work out the details, you can show an explicit reduction between the polynomial method and our new method. So our new method, just like the multiplicative adversary method, it works for every possible input distribution. It also works for exponentially small success probabilities in epsilon, and we can use this fact to allow it to satisfy a strong direct product theorem. The problem, however, is we don't know yet how easy we've just made it to bound this progress. So at least instead of going from some arbitrary C, we now have something that really resembles the compressed oracle technique. And in the case of like random input distributions, we can make this mapping very formal, and we can really show how to construct these eigenspaces and get the desired bound. The problem is we still don't know how to do this in more complicated input distributions. So the problem is still not fully resolved, but we hope that this construction kind of gives a nice, clear way forward, that maybe looking at the multiplicative adversary method is the right way to generalize the compressed oracle technique. So to quickly summarize, our new technique captures all known applied instances of the multiplicative adversary method. But even despite it still capturing everything, we put so much structure onto it that we get a much simpler progress bound. And this much simpler progress bound still admits strong direct product theorem. It allows us to capture both the compressed oracle technique and the polynomial method. And for those that are familiar with it, it even captures another recent approach that did successfully generalize the compressed oracle technique to permutations, but that uses a lot of representation theory. And we show that, in fact, it can be captured by our method as well. Further showing that, indeed, generalizing to further input distributions, this might be the way forward to do it. So with that, I would love to thank you for your time and attention. And if you have any questions, you can always reach me here, or you can find the paper here as well. Thank you.